Welcome everyone to this brief announcement, Efficient Load Balancing through Distributed Token Dropping. This is joint work with Sebastian Brandt, Jörg Rübicki, Jukka Suomala, Jaro Witto, and myself, Barbara Kellner. We look at load balancing in the local model. Each node of the input graph is a computational entity, and each edge is a bidirectional communication link. Computation proceeds in synchronous communication rounds, and the message sizes are unbounded. Throughout this presentation, n denotes the number of nodes, and delta denotes the maximum degree of the input graph. We have two kinds of nodes. We have clients and servers, and we want to assign clients to servers in such a way that each client has a server. Now, in more detail, this problem is known as semi-matching. The goal of an optimal semi-matching is to assign clients to servers in such a way that the sum of the loads of the servers is minimized. You can see that we have the clients here on this side and the servers on this side. And each server has a load. The load is nothing else than the number of clients assigned. In this work, we are not studying the optimal semi-matching, but the locally optimal semi-matching, which is also known as a stable assignment. What do we mean by that? In a locally optimal semi-matching, no client has an incentive to unilaterally switch servers. This means no client profits by switching to servers and getting a server with a smaller load. Let's look at a concrete example. We have clients with access to servers. This is now a semi-matching, and we can ask, is this locally stable? And the answer is no. As you can see, the node down there, which now turns to orange, has an incentive to switch. It's currently assigned to a server with load 3, and it has access to a server with load 1. If it will switch, then it has a smaller load. Please note that it only makes sense for a client to switch if the difference of the loads of the servers is at least 2. Otherwise, the client will be assigned to a server with the same load, as the switching increases the load of the new server by 1. This new assignment, as you can see it now, is locally optimal. It is even an optimal semi-matching. You can never do better than each server having the same load. Let's look at another assignment. We can ask again, is this locally stable? And the answer is yes. As you can see, a locally optimal semi-matching is not an optimal semi-matching. But it was proven by Chikrinov et al. In 2012 that this is a 2 approximation. What is the state of the art of distributed semi-matching, and what are our contributions? Chikrinov et al. Find a locally stable semi-matching in O of delta to 5 rounds in graphs of maximum degree delta. We improved this upper bound by delta to O of C times delta to the power of 4, where C is the degree of the client nodes. In the special case of the client nodes having degree delta, this leads to the same bound. But in general, we assume that clients have much smaller degrees than the servers. We additionally proved a lower bound of omega of delta. As we also study the locally optimal semi-matching, we have the same 2 approximation to the optimal semi-matching as found by Chikrinov. How do we save this delta in time? Instead of starting with a random assignment and then fixing the assignment step by step, which can lead to a long tail of fixing, we carefully add new assignments and phases and make the graph locally stable after each phase. Our general idea can be phrased like that. We start with an empty assignment. We temporarily assign at most 1 more client per server. We balance the additional load with a new technique, which we call token dropping. And after that, fix the assignment. We do repeat this process until all of the clients are assigned. Let's get back to the example. The unmatched clients propose to their servers with the smallest load. Ties are broken arbitrarily. This can look like this. Then, as a next step, the servers accept 1 proposal temporarily. Again, ties broken arbitrarily. Then this balance step shows up but as you can see, there is nothing to be done at the very moment, and these assignments are accepted. We continue with the process, and the unmatched clients propose to their server with the smallest load, maybe like this. The servers, again, temporarily accept one proposal, and the balance step is invoked. Again, so far nothing happens, and the assignments are accepted, and the load of the servers increased accordingly. Now we continue. The clients propose, the servers accept. And now something happens. As you can see, this node is now unhappy. It has access to a server of load 1 and is not locally optimal semi-matching. We now take a closer look how the balance step works. So, as a first thing, I want to talk how we build up the token dropping game graph. So all of the servers are represented as nodes in our new graph. A node also has a level. This is nothing else than the load of the server before accepting temporarily the new client. All servers that share a client with a server that has a different load are connected via an edge. All the temporarily assigned clients are represented as tokens. This can look like this. Now, this is not from the same graph we just looked at, because I wanted to have a bigger example than this would have given us. The rules of the game are pretty simple. Tokens traverse the edges down to unoccupied nodes, and any edge can only be traversed once. Let's have a look how our algorithm works in detail. The unoccupied nodes who have at least one parent with a token propose to this parent to take the token. Again, ties are broken arbitrarily. Nodes with tokens take a proposal from a child, ties broken arbitrarily, and the token is passed down this edge. The edges are removed from the game and the process is repeated. The children propose, the parents accept, and the tokens are passed down. This is just repeated on and on until no token can pass any further anymore. While this process is pretty straightforward, the analysis of it was a bit trickier. But now, how do we get from this balancing step back to the original graph? So we do it like this. Traversing an edge is the same as reassigning the respective client to the corresponding server one level down. Servers that end up with a token have an increased load in the original graph after the token dropping game. And the resulting graph is locally optimal again. Let's quickly talk about the analysis of our new technique. The token dropping game can be solved in O of L times delta to the square and has a lower bound of omega of L plus delta. Keep in mind that L is the height of our game. And in our special application with the semi-matching, we know that L is also bounded by the load of a server, which is also bounded by delta. So we also show that any algorithm that solves the token dropping game in T rounds with the parameters L and delta can be used to find a stable orientation in O of delta times T rounds with the parameters delta and delta. Plugging in our findings, we have an algorithm to solve locally optimal semi-matching in O of delta to the power of 4. That's already all of it for this brief announcement, and feel free to contact any of us if you have comments or questions. Bye!